Okay, we're going to continue on here. Chapter 15 we got into. Again, chapter 15 is not too long of a chapter, but it does cover some interesting topics, including what we got into last time, which is KSP, that we can add to our ever-growing list of K values. Remember that KSP is really for things that are typically insoluble. So if you think about sort of your solubility rules, these are typically for ionic guys that are thought of as being solids. When we write these sort of reactions, it is always sort of this direction. We have solids on our reactant side, and they go to aqueous ions on our product side, positive, negative, guys. And that means that typically speaking, when we do our KSP expression, it is just the products. So it's usually just our products here. We usually do not have our reactants, but we do it like any other sort of equilibrium expression, which is we do need to obviously use the coefficients as the exponents and so forth. Now, there's sort of two ways that we do these problems, and you can use an ice table, and you should in certain cases for sure. There is a difference that we actually use S's is kind of the letter that we sort of choose, and that stands for the molar solubility. And that is the molarity, obviously. And we also look at sometimes what the solubility is in grams per liter. And remember that if you're going from molarity to grams per liter, that's the molar mass. That's going to be sort of that conversion factor that allows you really to go from moles per liter to grams per liter of that particular compound. When you do solve for S, though, typically speaking, it is the solubility of the entire product or the entire compound itself, as stoichiometry will work back the same way. All right, so we did an example at the end last time. We saw something like silver chloride was only like 0.02 grams soluble in 1,000 milliliters of water, which is not very many. So I think this is where we left off. So let's give this one a go. We're looking for the aluminum 3 plus concentration in a solution of aluminum hydroxide. That's the KSP value there. Okay, so let's take a look at this. So once again, typically speaking, these type of problems, as we talked about last time, if you're pretty much only have the KSP given to you, you should probably definitely do an ice table approach. As we also saw last time, even if you're doing sort of the other type of problem, you should probably also do more of an ice table approach. This is aluminum hydroxide, which I know will be a solid because frankly, I see a KSP value. So that's a pretty big hint that I will know that I will be a solid. This is going to break apart into aluminum, and we will get 3 hydroxides in this particular case. Initially here, we're going to start with 0 of these guys. Change is going to be plus S, and this is going to be plus 3S. That means when we get to equilibrium here, we'll have S and 3S in this case. Questions on the ice table. We could write our KSP expression here, which would be the concentration of aluminum times concentration of hydroxide. Once again, we do need to cube it because of the coefficient that's there. That would equal our 2 times 10 to the minus 32. We're going to obviously take our equilibrium line here, and we're going to put it into that expression. And that will essentially give us S times 3S. Remember, we still need to cube it as well. And that will equal 2 times 10 to the minus 32. We also need to make sure that we cube the number, which most people miss. So that is going to be like a 27s to the 4th as you go 3 times 3 times 3 and not just the letter. So you want to make sure that you actually do the number, very commonly missed by people. Will equal our 2 times 10 to the minus 32. Clearly at this point, we're going to divide the 27 to the other side. And that's going to get us we got like 7.407 times 10 to the minus 34. We're going to take the 4th root here of that number there. And again, on your calculator, if you happen to have a button that has that, you could use that button. If not, you could take the number and put it to kind of the caret and do 1 divided by 4. We'll also do the 4th root for you if you do not have that button on your calculator. So let me actually find mine here. There we go. Yeah. And if you do that, that will get you a S is equal to, I'll call it 5.2 times 10 to the minus 9. First off, any questions on that there? So again, if you take the number to 1 divided by 4, that'll give you the 4th root. 1 divided by 3 will give you cube root. 1 divided by 2 will give you the square root. So if you don't have that button, that's again a workaround. In this case, we are looking for actually the aluminum concentration here, and that would mean that the aluminum at equilibrium does equal S, which means that should equal, we got there 5.2 times 10 to the minus 9 molar. By the way, we could also, if we wanted to, figure out the hydroxide concentration at this point, and the hydroxide concentration would equal 3S. So it would be 3 times that, 5.2 times 10 to the minus 9. And that would give us our hydroxide concentration of, looks like something like 1.56 times 10 to the minus 8 molar. That might be good because if I have the hydroxide, I could, if I wanted to, right, calculate the pOH, and I could calculate the pH of this particular solution by knowing that as well. So that's some other information that, you could calculate if you wanted to by knowing that hydroxide concentration. Any questions on that there? All right. So can we use KSP values that we find in tables to help us determine, for example, which substance would be perhaps more soluble or less soluble if we had a couple of those guys together? The answer is yes and no. You can use the KSP values in certain situations to make a prediction on solubility, but in some cases you cannot. And really what we're talking about, for example, is if we had something floating around in the solution, like some chlorides, maybe some bromides, and you want to add something to it to precipitate out these guys. We can use, in certain cases, the KSP values to make a prediction as to which one we would expect to actually precipitate out first versus the other one. Now, if we take something like all 3 of these guys are silver iodide, our copper 1 iodide, and our calcium sulfate here. And if we take each of these guys, when they break apart, we will get a silver ion and an iodide. We will get a copper 1 ion and an iodide. And we will get basically a calcium and a sulfate. Now, when we compare how each of these break apart, they all break apart into 2 ions. So they all break apart basically into the same 2 ions, which means essentially you'll be doing the same math for all of them if you were going to calculate the solubility of it. And that means that you can use the KSP values to compare solubility. Now, the largest KSP value will be the most soluble. So if you looked up the values for these 3 guys, you would see calcium is the largest KSP value and silver iodide is the smallest. That goes back to our normal sort of idea of equilibrium. That is, if we have a large value of K, that means we mainly have products at that point, which is on the right-hand side and should be aqueous ions floating around. If we have a small value of K, that means we should mainly have reactants, right, at equilibrium. And that in the case of KSP would mean you have a lot of solid present at that point, rather than if you had a larger value, it would be more soluble. So if you want to compare sort of solubility of ionic compounds and you have KSP values given to you, the only place where you could actually compare them directly just using the KSP value is if they break apart into the same number of ions. So they break apart into 3 ions each, then you could compare them. If they break apart to 2 ions like here, you could compare them. But you cannot compare compounds that break apart, say, into 2 ions and ones that break into like 3 ions or something like that. Because of the different number of particles, it affects your calculation. So to sort of demonstrate that, if we look up, for example, in a table, the KSP values for each of these 3 things, copper 2 sulfide, which again, when it breaks apart, you're going to get a copper 2 ion and a sulfide ion. Our silver sulfide, which also when it breaks apart, you will get 2 silver ions and a sulfide ion. And lastly, if we look at our bismuth there, when that guy breaks apart, we're going to get a bunch of stuff. You're going to get a couple of these guys. So this guy basically produces 2 ions. This guy is 3 ions. And this guy is a lot of ions, 5 ions. Now, when we go to compare these guys based solely on KSP values, we actually see that this guy has the largest KSP value. This guy has the smallest. And if we went by that sort of estimate, we would actually predict that this guy would have the greatest solubility based on the KSP value. But when you actually do the calculations for each of these guys, like we did before with your ice table, your S's, and solve for the molar solubility, what we actually see is the guy on the bottom actually has the greater solubility. And it's actually the guy on top that actually has the less solubility, or the least solubility, when you actually do the calculation. So this demonstrates that if you are comparing things that do not break apart into the same number of ions, you cannot use the KSP values to directly predict which one would be more soluble or not. You actually have to do the calculation to make that prediction. So you can't use your KSP values. Any questions on that there? All right. Well, clearly we come to the end of our day here today. So that's good.